Anyways, so this is presentation is about the internal structure of GPT-2 because I found that a lot of explanations of GPT-2 um, assume a certain level of knowledge, and it's really hard to go from like pop sci video all the way over to common good descriptions, explanations of GPT-2 that you might find on the internet. So I hope I do it better than everyone else, and I am always open to feedback. Anyways, so yeah, like I said, a, um, a lot of the examples I'm going to be using are generally like sort of wrong in that I will be using like extremely short tensors, like three or four numbers long, whereas in reality, the smallest model, which I'll get into that, all my examples will be from the smallest model of GPT-2. But yeah, the smallest model uses like 768 long tensors for most of its operations. Anyways, I'm skipping over a lot of stuff like normalization, where you make the mean of every tensor, every matrix, zero, and like I think also set the standard deviation to a certain value, something along those lines. I'll be glossing over that because it adds like a lot of cognitive load in helping to understand, in trying to understand GPT-2. Anyways, I use a lot of baseball analogies. Unfortunately, I don't actually know that much about baseball. I have no idea what a designated hitter is. I know words like first baseman and like outfielder and like hit percentage, but that's about it. So if I get anything wrong, feel free to yell at me. Anyways, like I said, existing primers on GPT-2 aren't very good. Wikipedia is notorious where anything mathematically related, it's like gives you a very precise and right explanation that's also incredibly difficult to understand for someone who's not like an expert in the field. And also, a lot of existing examples tend to focus on like the original transformer architecture. They'll use words like decoder and encoder that like don't actually make sense in the context of GPT-2. GPT-2, by the way, is a decoder-only model, but the decoder does encoding and decoding at the same time. And like the structure of a decoder and an encoder is also almost exactly the same. It's just due to like because it technically contains like the value and query matrices, it's considered a decoder, but like using that word actually just confuses people. So I won't use the word decoder in my explanations. All models are wrong. Some models are useful. So yeah, I will like some things aren't like technically super pedantically correct, but I have a certain number of wrongness points, and if you use too many wrongness points, like your model starts breaking down and it actually starts making less sense. But I hope I'm using an optimal number of wrongness points to help you like actually get a gears level understanding of how a transformer like GPT-2 actually works. And so, you don't say something embarrassing when talking about GPT-2 on the internet to someone like Gwern, who I look up to, uh, because I've definitely, after doing this whole project, I definitely realized I've made like some serious mistakes in past conversations about GPT-2. Anyways, what did I actually learn? Well, I'm actually really surprised by how transformers are structured. So the big issue that transformers seek to solve is that when you have a really long context, like not even really long, let's just say you have 100 words, right? If you have a piece of writing with 100 words, any one of those words may get context from any one of the other words in the entire context window. So that means like you are going to have an n squared, where n is the length of the input. You're going to need an n squared number of attention operations. Um, so the way that GPT-2, well, the way that transformers solve this problem is that attention occurs solely, like the really big, what's the word? Combinatorial operation, the attention mechanism, where it's you actually have to do an n squared number of attention mechanisms per transformer block. That only the attention mechanism only takes place through dot product operations instead of matrix multiplication operations. So it's like instead of n cubed, which would you would need for like matrix. Wait, yeah, I think it's something like n cubed for matrix multiplication operations. You wait, no, actually, I think I'm getting that wrong. No, it's m squared. So instead of like n squared m squared big O, you get n squared m big O. So that's actually a huge deal. And in an earlier draft, I actually had like completely different conclusion, but it turns out if you do the math right, it's something like the overhead for per token only exceeded by the attention mechanism once you have over 50 tokens for GPT-2 small. That number actually goes up as the models increase in size. Anyways, I now know Kung Fu. Previously, I had really tough problems trying to figure out how to do interpretability stuff, but now I'm just like, oh no, yeah, no, I know how to do that stuff now. Anyways, refresher. I basically used vector and one-dimensional tensor interchangeably, right? A vector is a one-dimensional list of numbers. It's like, yeah, you can think of it as a direction in m-dimensional space where m is the length of that list of numbers. A tensor is like an n-dimensional vector. A one-dimensional tensor is a vector. A matrix is a two-dimensional tensor. Anyways, dot product is you take two tensors of the same dimensions and then you multiply you multiply the two numbers on every individual index. Actually, no, that shouldn't be divided by three. I'm sorry. I'm not sure why I added that brain fart. Okay. Matrix multiplication. I actually don't want to explain it, but I hope you understand what matrix multiplication is. But yeah, quick overview. So what is the information flow in a, oh, by the way, I might have not, I don't think I actually explicitly said that I'm welcome to questions at any point. Feel free to interrupt me at any point. I actually really do welcome questions in the middle of presentations because like I really want to make sure that that there are like no obvious misunderstandings and it helps me engage better with the presentation. So yeah.
Are
Anyways,
you sure your dot product definition is correct?
What? Dot
If you
product
go back,
definition?
yeah, if you go
Yeah.
back to
Oh
that,
crap. Yeah. No, you're right. It shouldn't be a vector. It should be those numbers added together. That is a catastrophic mistake. I'm so sorry, guys. Wow. Okay. My my bad. My bad. But yeah. Anyways, you go from a string, right? Like French fry. You tokenize it, where you convert each word or part of a word into a number out of like 50,257. And then uh, I actually don't remember. I think it divides into like 700. No, no, it would be like it's probably like the tensor length of the longest number times like I don't know, 128 or something like that. A lot of these numbers are arbitrary, and a lot of these numbers occur like you see the same number occur multiple times throughout GPT-2 small, like the number 12. They have 12 transformer blocks and also 12 attention heads per transformer block. That doesn't actually mean anything. It's just happenstance. It's just that they picked a number. It worked well. They probably picked other numbers that worked less well during early phases of training. That's just how machine learning works, trial and error, basically. Okay. Anyways, so you take each token, right? And then you look up a token embedding. So it's like the word French is converted to 4141, and then you look up that particular row in the embedding matrix, and that plus the positional embedding, which is like based on which index it's on, is you add those two vectors together, and that becomes the the final embedding for that particular token. That's the final token embedding, right? And then you get one of those for every token you insert into the model. And then at every transformer block, you input and output the exact same the exact same dimensional matrix. Uh, yeah, that ends up being really convenient because like you don't have to do very many conversions. And yeah, anyways, by go on. Mhm, mhm. Uh, well, each one of those numbers is basically a concept. It's like how French a particular word is. I like didn't really have time. I had a bunch of other stuff in my life going on. I was actually going to go through the embedding matrix and look at what each one of those floating point numbers mean, but they generally link to a particular concept or like some combination of concepts. Like you can't just have a binary for how French something is. Like that there are actually gradients, but also at the same time, you're absolutely right. It turns out when you go to 16-bit precision, like you basically get the same level of performance. They probably just use 32-bit precision because that's like the default in whatever framework they were using at the time. Okay. Uh, right. And then once you get to the final output of the final transformer block, you just take the very last representation. You just take the representation of the very last token, right? Like the last 768 floating point number vector. And then you do like dot product operations on that with the original embedding matrix, which is the one that converted the tokens to the embeddings. I'll get to that later. Like this is super confusing and makes zero sense. And like a lot of people will try to explain it. I actually get this part wrong because it's like the underwear gnome part. It's like, okay, so I have like this 768 by 1024 matrix. How do I get like my final answer? It's like, well, you take the final token and then you like run dot product search for the embedding matrix. What? It doesn't make any sense. I'll try to explain it the best I can when I get to it. Anyways, side note, I previously made a claim like a couple months ago that the context length of a transformer is set in stone, right? I made that explicit claim. Turns out that's not really true because first of all, the embeddings are like added to the token embeddings. So it's like that 768 long vector contains both the positional information and the token information, which means that you can actually go beyond the original context length, right? And if you look at that particular chart on the top, oh, you guys can't see my mouse. Okay, so it's like you. Okay, cool. So the positional index. So yeah, this is like a learned positional embedding for like they have one for each of the 768 floating point numbers. But yeah, like they all tend to look like sinusoidal function. They all look very sinusoidal, and also there sometimes is like very particular activity right at the beginning or like right at certain indices. But it's almost always the beginning. So like you can extrapolate this and probably extend for like GPT small too small to like 1050 context length instead of just 1024. But like as you see on the right, the perplexity starts skyrocketing, even with a handcrafted positional embedding that's specifically meant to make this thing easier. But yeah, this actually points to a super important part of of transformer networks in that like the index of a particular vector isn't really relevant to how it's processed. Like all the information to where it's supposed to be in like sequence is contained within the vector. So it's like that's actually ends up being really convenient. The only part where the index actually matters is for the very final output, the very final transformer, where you need to take that particular vector to get your final answer. Okay. Mhm. That's actually not one. Sorry, 1 second. I have a phone call. Okay. Sorry about that. I was like, yeah, I was just getting like my takeout guy just called me there. Actually, that's not what I was going for. Like, they're actually doing something weirder because it's like they're both doing like regular attention mechanism stuff, like the stuff that's really easy to understand, right? Like fry becomes like fry, but in the context of French fry. Like that's the normal stuff people find easy to understand. But also they're funneling like all of the information on the probability of the next token into the very last input token index. Like I understand this makes zero sense because it doesn't make any sense to anyone, but like that's just how it's structured. So it's like the fact that red has a big impact on like the probability of next word, that's like baked that's like not actually part of that. It's like you can build an encoder decoder model that actually outputs things in a completely different way, and like it would still put strong emphasis on the very last token anyways. But you are kind of right in that it's like a very convenient place to put all the information because it's like it does like statistically have a huge amount of impact on the very next word. And I guess that like that actually does make, given the structure of everything, it's probably better to put it there as opposed to literally anywhere else, but not by much probably. Okay. Mhm. Mhm. Well, I mean that you have to remember that this is only one out of 768. So once you like take all the information from like all of like this is the really interesting part because for previous transformer models they just restricted the positional embedding information to the very like um last two floating point numbers, but it turns out it basic like after the very first transformer block, it basically spread all that information out through of the all of the floating point numbers in ways that vaguely resemble what's going on here. Like, and I'm not really sure if you're right or not, like that, but that's like my understanding of what's going on here is just a lot of that. is probably noise, or maybe it's like not even noise. It's like two sinusoidal waves like overlay on top of each other, like it's a sum or something. I don't know. Like neural networks get really weird. Oh right. Oh yeah, shit. You're right. That's right. My bad. My bad. Okay. Yeah, it can make sense. Anyways, I explained this part earlier. Tokenization, it's like they start with a certain number of initialized tokens, like English characters or raw bits um, sequences, and then they like find the most common pairings, like bigrams of token combinations. Like French fry is a bigram, but that can actually be converted into a single token because there's a space in between. It's complicated, not super relevant. Moving on. Okay. Mhm, mhm, mhm. Yeah. Yeah. Basically, this is very information theory, heavy stuff. Like that's basically what they were going for. But it ends up being super inefficient, and also like you don't really want it to be super duper efficient because you end up with like really weird glitch token stuff because your like input data is like 5% like porn spam. And yeah, anyways, you're right. Like that this is kind of optimal in a certain information theoretical sense, but also not really. Uh, yes. Uh, yeah, I think that's like it was just based on very simple Shannon information theory concepts, I think. Anyways, moving on. So the fundamental unit of processing GPT-2 is the 768 long vector. So what actually, like I said, what actually happens is you take the token value matrix, you get it, and you pull out like the 1057th row for run, and you see the two runs have the exact same token embedding here, but the positional embeddings are different for the two of those. That's how the model distinguishes between two instances of the same token. But the positional embeddings also don't care about what tokens there are. So no matter where your input is, the added positional embedding is for the token on say index two is always going to be the exact same. It's always going to be the exact same number, and then you simply add the two numbers together, and yeah, that's it. That you now have the 768 long vector that is the fundamental unit of processing in GPT-2. Why is it called a transformer? Well, it transforms inputs by giving them context from surrounding words, tokens, whatever. Uh, this is, yeah, I think that's just basically what it means. My French fry example, fry, um, is there are different types of fries. So the inputs are like a platonic form of the word fry. It's like a superposition of all these different concepts that come to mind, like in a human. We say the word fry. It could be a verb, it could be a noun, it could be curly fry, it could be French fries, all kinds of stuff. And once you add the information from the word French, it's like alters the word fry, but like also it goes back and forth, like down the transformer blocks because French can mean different things, and like French in the sense French fry, like I think this particular two token example doesn't stabilize until like two or three layers in. So like you actually do need the depth in order to get uh, get stable, consistent um, context, basically. So for yeah, mhm. Like can you what was like the rough direction? Like what was mhm, mhm. Um, kind of like they did this to make things easier to conceptualize, and also because like they were trying to pick random numbers. They were like, you know what, let's just use 768. You know, we use that a lot. Like, that way we can just have square matrices all the way down, except for where we don't. So, mhm. Oh yeah, absolutely. Like GPT-2 is not like this massively optimized thing. Like the ground math of like the attention mechanism is very optimized. It's super cool. It's incredible that it works as well as it does. But like the actual stacking of transformer blocks, how big they are, that's just like they were like, you know what? That looks pretty cool. Let's just stack like 12 of those, see what happens. And then they were just blown away by how well it functioned. But yeah, there's like huge amounts of play, a huge amount of place to optimize in GPT-2's architecture, and they went and did it. They went and built GPT-3 and all that stuff. So yeah, it is very suboptimal, but it's incredibly easy to understand because like it was built to be easy to understand. Does that make sense? Okay. Anyways, so let's have an analogy. Okay. Let's say we have a San Francisco baseball team, the Clerics. Unfortunately, the entire team is gone. Tragic accident. They were in the wrong place at the wrong time. So now they have to assemble a new team, right? Unfortunately, the players in the new team have literally never played together before today. They're also missing a player who they will have to figure out who to hire as they practice. And that is the entire point of this exercise. You have a bunch of people who never met before. They don't know how to like cooperate and form a coherent coherent game plan, and they have to figure out which player to hire out of a total of 50,257. So that's a problem. Anyways, knowing this, well, no, that this isn't like a large language model. This is like the positional embeddings correspond to like actual baseball positions, and like the player names, each player's name is like one token, and there's like 50,257 players. Like I know like this baseball analogy can get a bit confusing, and like I jump between different levels of abstraction, so if it's ever unclear, just point it out. Anyways, so yeah, they have to moneyball the hell out of all of this. And so the embedding for each player is like all of their baseball stats, right? And once you add the player embedding and the positional embedding together, you get like a vague idea, this vague platonic idea of, oh, this player in this position has these characteristics. But like those characteristics are going to change massively once the team is assembled and like the players start influencing each other. And very importantly in baseball, like if the same player can be assigned to like different positions, depending on how the team is doing on their opposite and stuff like that. So like, Marco Rubio may have a nominal position of first base, but in reality, like, he might be playing like third or outfield or whatever, stuff like that. And that's like the messy reality of natural language. And yeah, it makes the analogy makes more sense the more I think about it. Anyway, so go on. Yeah, yeah, and there are some statistics that are obviously like going to be better than that obviously have an ordering like I don't know hit percentage, but it's like God, I don't want to get into a rant about statistics and sports statistics, so I'm just gonna move on. Anyways, so each transformer block is like a day of practice, right? Uh, they're in deep trouble. So, anyways, each day is transformer block, and each attention head is like a practice session. And in each practice session, each player has 2 rounds with every other player. One as a pitcher and one. Okay, so this is me trying to define the attention head. The attention head. So, like, well, okay, I'll just read my description. So yeah, the idea is something like this. So before each session, you take the 768 number. We're going off of the very first attention block. The very first transformer block. Things start getting really messy as you go down. So yeah, the very first transformer block, right? So for before each session, the coach comes and goes through all of these 768 numbers and extracts information from those numbers and compresses it into a 64 long vector. Um, they only extract information relevant to a particular topic. That is the focus of the attention head. So it could be something like speed, which could be related to leg length, age, muscle mass, stuff like that. It could be pitch speed, which has other variables related to it. But yeah, it's like you pull out key, query, and value vectors, all 64 long, from each player's 768 long embedding vector. All right. So during each round, you have the pitcher and you have a catcher. This is like metaphoric. You can think of whatever you want in your head, but it's like the pitcher is the one who's throwing the concepts, and the catcher is the one whose like concepts are going to be modified by the pitcher. So what happens first is you compare the pitcher's query vector with the catcher's key vector. You just take the dot product of those two vectors, and you get a single floating point number. That is how much the pitcher's the pitcher's sorry, that's how much the pitcher should influence the catcher in this particular concept. So in actual baseball, it's like, okay, so you have player one, let's say Marco Rubio, and he has certain characteristics that causes other players on his team to go faster if he is also a player. Maybe like he's just a really energetic guy. Maybe, he has amphetamines. Who cares? The thing is, like, So Marco's speed will influence everyone else's speed to various degrees. And does that make sense to you? Mhm, mhm. Okay. So then, yeah. So yeah, the dot product is the magnitude. How much should the um, picture's value uh, vector on this particular attention head? How much should that affect the catcher's value for this particular attention head? So you multiply the pitcher's value vector by the dot product that I just mentioned before, and that's yeah. So the once a round ends, the catcher adds up all of those value vector times dot product, whatever. He adds up all of those sums together, and that is the output of that particular attention head. Does that make sense? Mhm. Yeah, basically. Anyways, where was I going? Right. So you take all the outputs of all the attention heads, like all 12, all 12 sessions for a single day. And then you get a 768 long vector, basically. Um, this is like happenstance. You could make this vector like way longer or way shorter. You could make it like 2000, you can make it like 50, but like they just decide to use the same number because it's more convenient and you don't have to do like all kinds of different reshaping operations. Anyways, so I'll have graphics later. Anyways, so once you do that, you pass it through a feed-forward neural network. It's basically like a dense neural network that's with one hidden layer. Very, very yeah, it's like a three-layer neural network. Very simple, easy to understand. I hope I'll go into more detail later. And also, very important thing to remember is that the key value and query matrices for every attention head that the same are the same. The same ones are used for every single input token. So yeah, yes, yes, of course. Okay, so after 12 days of practice, this is the like weird, difficult to understand part. The team captain, who's basically the very last token in the input, he goes through all of the players available higher, and then he finds the one that plays most like him personally, in the context of his team. So, he takes the dot product of his embeddings with every single player available to hire, including the ones already on his team, and then gives the highest scoring ones as his recommendations. I hope this is super confusing to you because it's super confusing to everyone else. Mhm. I mean, I mean, it's um like you have to engineer the entire system to get that outcome. Like if you train this entire like transformer stack to get that outcome, basically what you described happens. But if you had trained it entirely differently, like if you had taken like the entire output, the 768 by 1024 up to 1024 matrix, and use that entire thing, fed that into a feed-forward network that collapsed everything back down to 768. If that's what you had done, it would be completely different. Interesting part is like the collection, the funneling of all the information from the entire context into that final token actually takes place mostly in the last couple of layers. Like when you retrain a network to do a different task, like predict the second to last token, where like, okay, so you have 10 token inputs, right? If instead of trying to predict the token after that, you try to get it to sorry. Let's say you have 10 tokens, right? You take out the very last token and then you put in 9 tokens, and the normal GPT-2 job is to predict the 10th token. Instead, if you take out the ninth token and you put the 10th token back, you can make it so that the task is actually to predict the second to last token without the information from the second to last token, but you do have the information of the token after it. It turns out when you actually retrain GPT-2 to do something like that, number one, it gets higher performance because having a word like having the word after a particular word gives way more context than having like the 10th word before that particular word for obvious reasons. But also like not very much happens in like the first couple of layers, only in like the last 3 or 4 transformer blocks, or some maybe even the last 2 transformer blocks where all the funneling happens. So crap, I think I might have gotten, yeah, that doesn't make super huge amounts of intuitive sense, but just like in general, the funneling mostly happens in the later in the last couple of transformer blocks. Mm. Uh, no, no, no. The thing is, like, everything happens at the same time, but like the proportions are different. And also, like, if you absolutely can make a transformer architecture where it only does like where the attention mechanism only adds context, and you actually do get like like that's what the original encoding decoding architecture kind of sort of means. Like the encoder is supposed to like use the attention mechanism to like spread out all the context and like give everything its context, so you get like the true meaning of all the tokens. And like it does conceptual normalization. I'll get into that later. Does that make sense? Yeah, and then the decoders like decode that into output probabilities at the very end. But like GPT-2 does everything at the same time, and due to a quirk of terminology, is considered a decoder-only network. Okay. Anyways, yeah, like I said, relatively late into the system. So, okay, Marco Rubio, he's Cuban. Obviously, he can play baseball. Hamane, probably can't, but for the purposes of this joke, let's just say he does. So, Marco Rubio's input vector is like this number, and then you multiply that by the key matrix, and you get like this query vector, and then Hamane's input vector is converted through the key matrix on that on the same attention head into like this, and then you calculate a dot product. Hey, I did it right this time. And then also, you pass Marco's input vector through the value matrix, so you get a value vector, and then you multiply that by the dot product. Right, and then you repeat all the other participants, including Jamene's, with their query and key vectors against Jamene's key vector for this particular attention head, and the sum is the output of the attention head. So what do you mean? You mean two concepts, as in the concept of Marco and the concept of Hamane? Yeah. Uh, uh, Not influences. It could be a one-way influence, right? Like maybe, yeah. So how do I put this? So it's like in order to understand how a player performs um, for a particular metric, let's say speed, you have to take the speed information of everyone, including that player, and then do math on it. And that's like okay, so let's say like this was like a difficult thing for me to understand as well, but it's just crap. Uh, Yeah. So, well, it's also just sometimes you need like a certain enabling factor. Like maybe you need a certain fast player on the team. That you having just a single fast player on the team changes the entire dynamics. So if you're the fast player, you also have to include your speed information. Otherwise, you won't be able to accurately understand how much all the other what is the final result, what your final speed will look like on the actual playing field, given the influence of all the other players. Like yeah. Mm. Right, yeah. Okay, I think the baseball thing has outstayed its welcome because like now we're talking about clones and like uh anyways. So Hamene's embedding is has been changed by experience. He is not just a platonic a platonic Hamene. He is like Hamene as he plays given the other players on his team, how he'll actually play after you consider all of the influences from the other players. And this process repeats like over and over for each what this process repeats once for every a transformer block. So it's like you keep doing this over and over again, and also there's like funneling into the very last token. And yeah, there's like magic. So here's like a mathematical example, right? So you have like, let's say you have two attention heads. Each attention head is of length 2, and also all the input vectors. The input vectors for all the players are length 4, right? So all of the inputs floating point numbers influence all of a particular player's key query and value matrices. So it's like, yeah. And Soren, like you can see it's two different green and orange colors, right? Okay, so this is orange, this is green, and those represent different attention heads. The math, I think I mentioned that earlier. So once you so okay, so V1, V2 multiplied by like the attention mechanisms, more like key one, key two, query one, query two, and also like key one, key two, and query five, query six for Mako. So like you add the results of that, like I explained the math earlier, and you get O1, O2 for attention head one and O3, O4 for attention head two. And then you feed it into this matrix structure and you get the output, which is of the same shape as the input. And also, very important to note, the tokens only interact with each other through the attention mechanism. There is no other interaction. Everything else happens alone. They also go through like the same feed-forward network. They go through the same value matrix. They go through the same key and query matrices. Like other than that, they're treated basically the exact same and pass through the exact same matrices, which is quite convenient when we're trying to estimate. Oh, and like there's like a bloom, like you go from 768 to 3072 and then back to 768. This is pretty common for machine learning. It just like I don't know. I guess it like helps you get some intermediate concepts and then collapse it back down into the desired shape. So yeah, let's just say yeah, yeah. Yeah. Well, it turns out that a lot of that is like due to number one, vanishing grade. Actually, yeah, vanishing gradients and stuff. And I will actually get more in detail about stuff like that for the transformer stacking parts. So yeah, why do you want to stack transformers? Well, here's an example. The Greek bird sold the French fry. The bird is a okay. So you're trying to figure out what the bird is. Unfortunately, a single transformer block doesn't get you quite to the right answer because it's like, okay, so we can get to French fry and we can get to like bird from Greece and also like some weird stuff regarding like French and fry. Like you don't get like a bird that can steal a French fry. You have to keep going down the layers because like fry isn't because at the end of the first transformer block, you only get to French fry, but you need French fry in order to unlock the concept of a bird that is like bold enough to steal a French fry, as opposed to curly fries, which I guess any bird can steal. It's a really bad analogy, but I couldn't find a better one. I'm really sorry about this. So yeah, it's like you have to. Yeah, go on. Yeah, yeah, something like that. I mean, I wouldn't have used a Wikipedia example. That makes things super confusing. Like, can you? I know this is kind of mean, but can you make a better analogy so I can make sure we're like on the same page? Mm-hmm. Mm-hmm. Yeah, it's a video game. It's a video game crafting system. Yeah, yeah, exactly. Okay. Uh, so yeah, that's it. Like if you understand that, you understand like the transformer blocks, you understand the attention mechanism. That's really it. At the very end, you just take the very last um, token embedding of the output of the very last transformer block, and you look at it, and you take dot product of that and all the different tokens, and then you normalize, and then you like normalize the sum to one. Like also maybe you take like the square root of them. Whatever. The point is, you have like similarity between the tokens and the final output, and like uh that's like an ordering, and you can sample from that to get your final token output probabilities. But yeah, using the square root is like pretty common because I don't know, it's just a quirk of like matrix multiplication math or whatever. So yeah. Okay. Is there any? Okay. So yeah,
Sorry, if I can I jump in here? I think
yeah,
I kind of failed to understand properly the why multiple transformers, like transformer blocks, are needed and how they combine. So like I understand this idea that like you're going to need some decomposition, but
mhm.
they like the analogy to like video games and putting stuff together, like it's not clear to me. So basically the first transformer kind of creates one sub component and then the other can does another and then the third one just kind of puts them together. Is that it? Or
Well, it's like, how do I put this? Sometimes two concepts. So let's say you have concept A and concept B, and concept C. So it's like only concept A matches extremely well with concept BC, which is like the output of an attention block with the inputs of B and C. But like it individually, it doesn't match well. So it's like for my bird example, let's say that in the world in this like thought experiment world, Greek and bird each individually have very little interactivity with fry. This isn't true, but thought experiment. So it's like
Mhm.
in order to get good compatibility, you have to go down one layer where you actually have like the composite idea of French fry available.
Gotcha. Yep.
And yeah, okay.
Yeah, okay. So basically like one of the transformers is going to like create, oh, French fry is a thing. Cool. So basically replace the idea of French and fry with the idea of French fry.
No, it's more like it's spreading it out. It's like fry in the context of French fry and French in the context of French fry. So it's like the French becomes more food oriented and the fry becomes more,
I
yeah, yeah, it becomes more French cooking oriented, basically.
I see.
Anyways.
Okay. Okay. So basically, kind of passing it through one layer of transformer, or like through one transformer, will kind of sharpen this thing. Like, oh, when we say French fry, the French, as you were mentioning, is food, and fry is French. Um, and then basically, there's a certain number of those, like in sequence, or is it like each kind of pairwise they go in parallel to kind of refine all these concepts, or yeah, I'm not sure how the whole thing
It all
gets put
happens
back
at the
together.
same time. Like, so yeah, every word undergoes the intention mechanism with every other word
Hmm.
in every single layer,
Yeah.
basically.
Uh, Sorry, layer or block here?
In every block.
Okay,
Sorry,
cool.
my bad.
No, no, that's fine. I may be misunderstanding. I don't have a good familiarity with it, but okay. So in each one, and that's kind of like how you get this, the 2D table that we've seen with like the hotness compared to other stuff,
Mhm,
of like words with themselves and others.
Yeah,
Um,
yeah.
so I see kind of, and this will happen kind of sequentially. So like one block, or no, you're saying all the blocks at the same time, and
No,
then what
no, no.
happens?
One block after another. The
Okay,
input, the output of block number one is the input for block number two.
okay. So it's like at every block, it's like refine what this might mean,
Yeah, yeah.
and then after a certain number of blocks, we're like, yeah, you kind of hope that you mostly got the meaning.
Yeah, and also like in the last couple of blocks, at the same time this is all happening, it's also funneling all of the next token probability information into the very last
Right, right. Okay.
tensor. Right. Okay,
All right.
cool.
Cool. That sounds good. Thank you. You can continue.
So yeah, right. Like I said, this is contextual normalization. Since like remember back in college when I was studying neural networks, they one very important thing they brought up is that if you normalize like animal images, like if you have them all animals all standing in the same position, a very very small neural network can have except like incredibly high accuracy in classifying those different animal images. Like all the hard work in terms of visual recognition is normalization, right? That's the hard problem of image recognition, and really it's the hard problem of uh, natural language processing. Like different words mean different things in different contexts. And like winnow-grand schemas, that's like this was a super hard thing for AIs, in the past. And uh, by the transformer architecture can be thought up as contextual normalization. It's like you make the implicit connections between all these words more explicit. What? Huh? Mhm. Uh, well, it's like imagine you have perfect zero ambiguity language. You said still when you say the woman has a knife, right? Like you would still modify the concept of the knife by okay, it's a knife that a woman holds, and the concept of woman as a woman who is holding a knife. Like there's always context. It's just less word ambiguity, but still like there's always context. Um, less than you might think. Less than you might think. For example, Chinese has zero gender. Well, not quite true. Like it has like third person pronouns that were introduced like 100 years ago. It all goes all the way back to Jesuits. But basically, like Chinese is a gender neutral language. Basically, but like third person pronouns written down. The written version of third person pronouns specifically are like slightly different. Um, and also like the second person ones are different if you're in Taiwan. Like it, and also we don't have any tenses. We don't like when we talk about time, we just say things explicitly. And that's like a general trend in Chinese language. However, with the same amount of language information, there doesn't seem to be a super big edge for Chinese that like is can be attributed more to this than to stuff like tokenization advantages. So ultimately, probably plays a role. Is it like really? Can you really see it on a graph? Probably not. That would. Uh, I don't know what it is. Yeah. I don't know. Like, it's like depending on how esoteric you want to get, like there are actually words that people made up just to be complex and mess with people. Like there's a specific type of noodle that's like hellishly like the character for it is hellishly complex as a marketing scheme. And this came about like 1,000 years ago. They like made a character just to sell noodles. So it's like yeah, it's 100,000, but realistically, like the ones in common usage is like 10,000. It really depends. Like there is pretty strong like um if you want okay, I don't want to go in tangents about literacy in China and okay, yeah, it is kind of funny. By the way, like I'm like actually kind of illiterate in Chinese despite actually writing complex technical like papers in Chinese because like I can't write Chinese characters by hand. And it's actually kind of scary because we're getting to the point where more and more Chinese people can't write words by hand. Like and it's like super embarrassing when some guy asks me to sign for like a package and he's just like, dude, don't worry about it. Happens to everyone. You can't write down basic words by hand. Happens to everyone. Anyways, I'm illiterate. Okay, so encoders first.
Another question on Chinese, well, not specifically Chinese, but just kind of understanding like languages. I understand that most of the, at least LLMs are trained on at least partially English. The architecture is the same, whatever language you train on, right? So like
Yeah, yeah.
like if there's some language, I don't remember which ones, but like have a verb, maybe Japanese to have a verb at the end or something like that. Like the actual humans listening to it have to, or maybe no, it's not German. Kind of have to wait to the end to know what the whole sentence is about. Do those
Mhm.
perform like all reasonably okay on the same architecture?
Oh yeah, absolutely. Like it's just like the original transformer architecture from attention is all you need. Like the encoder architecture is sometimes used in encoder only networks where they just like do sentiment analysis or translate like a sentence from Japanese to English. But yeah, like it's just a pretty simple like transformation operation. Like linear, it's a pretty simple like basically it's linear transformations. You can do that in like one or two transform. I don't think you can actually do it in one or two transformer blocks, but it's like you get my point. It's a very simple
Yeah,
operation.
there's not a whole lot of cost from one language to the next, and like
Not
building a
not
Sankey
really.
language would not.
Like yeah, like the really hard part in natural language processing is like actually processing language, not a particular language. You're like trying to process the human's thoughts that they're expressing through language. That's the hard part. The
Okay,
word that yeah, the grammar and stuff like that, like and word sequencing, that's like the easier part.
gotcha. Cool.
Okay, so I actually went and calculated the parameters for all for I went and like to try to account for every single parameter in GPT-2. I mostly succeeded. Uh, like there's some math for that. I uploaded the slides. You can look at that. Unfortunately, like there's some like weird ones like these two. I'm not entirely sure what they're responsible for, and these two, like I think that these are filled with real numbers, and like this one is only positive numbers that go up to like that like go over one. This is like includes negative numbers since it's like bounded to between -1 and 1, and like you see the same pattern between these two. This is positive, this is like positive and negative. Like I don't know what's really going on with those. I was gonna like dig into it more, but I got tired and I didn't have time. So yeah, let's see. Like I said, once you get to the very end, you take the very last token, uh, vector embedding, and then you take the dot product with the embedding matrix, and you normalize and everything, and there's all kinds of sampling techniques. And temperature means like how much you bias things towards the highest ranked outcomes. At temperature equals 0, it selects the best match 100% of the time. There's like search algorithms, stuff like that. So that's that. That is my entire presentation. Wow, it's been like an hour. Any questions? Mhm. No, no problem. Mhm. Yeah, yeah. Mhm, mhm. I think there's like a I'm not entirely sure this is I'm not 101% sure this is the case of GPT-2, but a lot of models have a start of sequence token. So yeah, you could just put in a start sequence token and then it just like generates based off of like stuff it's seen, but it's like biased towards the beginning of like news articles and stuff like that. But yeah, there's a reason they pay very strong attention to like the very the very start of the sequence, like the sinusoidal thing I showed before, where it has a very strong reaction to the very beginning. Yeah, yeah, you could do that. Mhm. You get the start of news articles and like whatever other stuff it's seen on the internet with, I think, a certain bias towards shorter things, with like shorter web page things, because of the way that like it's like training inputs were batched, where like where like it will take um let's say you have a web page that's like three context windows and length. So you like when you're doing actual training, you take like the first 1,000 tokens and you train on that, and the second thousand and third thousand. And but like if you only have 500 tokens for a particular web page, they generally don't. I'm not 100% sure on this, but I think they don't like squish two web pages together. They're just like take the entire web page and use it as the input. So it's like biased towards certain shorter web pages. But other than that, like yeah, it's just a general what commonly starts in its training data. How do inputs start in training data? And it's generally like shorter web pages, basically. Uh, it's never seen a token before the start of sequence token though. And also like oh see now I'm concerned because it's like I don't want to be mean, but it's like you the entire model is trained on predicting on like funneling all of the next token information onto the very last token. So it's like if you want to predict the token before a sequence, you'd have to retrain the entire network. Yeah. Mhm. 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 Uh, Agenticness as an agenticness of particular tokens. Yeah, I could totally see that. Like, is this sentence representative of an entity, an agent with high agenticness or low agenticness? Yeah, I would definitely expect to be able to find something like that in a bigger model, or maybe even just in GPT-2 itself. Uh, Well, I mean, AI takeover is like pretty common fiction trope. Like, yeah, I would expect it to be represented as a concept in there. And, if it starts talking like a something that's trying to take over the world in such a way that's visible in in our interpretability tools, yeah, that's definitely a red flag. Would people actually do anything about it? I mean, it's like I would imagine the result would be like, wow, it could represent a bunch of different things. Let's like maybe revert to the last to the last update before it started doing this sort of stuff, or maybe they'll just train it away. They'll most likely they'll be like, yeah, it's kind of weird. Let's train away that behavior. Yeah, definitely. Uh, I mean, you would be exam. What? It's like the properties of written an agent's written text aren't necessarily indicative of the agent's future behaviors. However, like you can look at um, the intermediate concepts, like why is this agent writing this stuff? Like, what is the causal pathway by which it produces this output? And if you get interpretability good enough, you can be like, oh, actually, there are these human understandable concepts behind why it's producing, why it gives these output token output probabilities here and here, and it's like, okay, well, we can actually like reverse engineer what roughly what is going on in its head and its thinking process, like to produce those tokens, and we can use that to predict its future behavior, like maybe even into like the far future for this particular interaction. So it's like, yeah, we could, but it's like it's not going to be as simple as sentiment analysis where the sentiment is take over the world or utility function. Like you actually have to do the engineering and figure out what's going on with the model to produce its output. but also but at the same time, obviously if like the Skynet, neuron, the Skynet attention head is like screaming, and but like the outputs are otherwise normal, and this all suddenly happens, and like there's like weird agentic stuff going on. Yeah, I should probably pull the brakes. Like obviously you should. Hmm. Well, yeah, for a particular concept. Hmm. I don't know. Like I don't have anything to say that maybe, but it's like my gut says that's not. My gut says that's not where the magic actually happens. Oh, and two things before they're super important. Number one, you can actually look at the intermediates uh, of like you can look at like the outputs of Transformer Block 3, and that way you can see like, oh, at every layer, how are these how is context information incorporated at each individual layer, because you can actually like run the final operation, the dot product operation against the entire like token embedding matrix. You can run that with the intermediate outputs. So you can say, oh, look here, this word like this particular token at this particular place in this particular transformer layer output um, is most like this concept. And I think there's been a lot of work in that direction. And I think that's pretty cool. And also, one very easy interpretability tool is you can just run interpretability on each one of the 768 vectors. You can see, oh, well, this vector corresponds to this particular concept. I was going to do this before, I ran out of time, but like that's the simplest tool. You can like actually just look at intermediates and see how they correspond to each one of the 768 floating point numbers, and you can like get a pretty good idea of what each one of those means by like mapping them onto like each one of the tokens, like which tokens have high values of this particular number and which ones have low ones, and it's like it kind of sort of works. Mhm. Okay. I mean, hallucination, bullshitting, those are all concepts. Like they have negative variance in human language. I don't want to taboo them, but it's like you have to understand how these things actually work, because um, it's like I'm a very good test taker. All right, I'm extremely good at standardized testing. Uh, if that has set me up for a lot of disappointments later in my life, all jokes aside, it's like the hallmark of a really good test taker is like being able to, number one, get a good gut feeling for every question, and number two, being able to bullshit exceptionally well. It's like it's not even bullshitting after a certain point. It's like, okay, I'm not 100% sure that I'm correct on this, but I'll pick the best answer. Like that's what actually happens when you quote unquote bullshit on a test. And it's and a lot of times like it's like, oh, you're subconsciously like pulling on these concepts, and it's like you're actually completely correct, but it's like it's possible to be like activate like this kind of like weird gut intuition that you might call bullshitting when you're wrong, but like it may be the case that most of the time when you activate that you're actually completely correct, and you're just like doing inference on like vague on like poorly remember things and like pulling the context together from everything you've ever learned your entire life. And like arguably that's like the highest level of human performance in terms of like uh, actually doing things, right? So I don't think it's completely fair to call it bullshitting because like that means you assume it's not bullshitting when it's right. But it may be the case that like being able to do this is what allows like GPT-2 to be as coherent as it is in the first place. Like it's entirely possible that the high performance of LLMs are fundamentally due to like this quote unquote bullshitting capability or good test taker capability. So it's like you can't really you can tone it down, but then that just means it's like it's less able to like pull disparate connections and like actually be creative and like actually like surprise people by how good of a model it is, you know. What I'm trying to say is, you know, actually no, that's not fair to the women I've dated in the past. I was gonna make a really like crude joke. Well, it's not crude, but like really messed up joke there. Anyways, keep going. Mhm. I mean, depending on the model and its tokenizer, like we might already be there. I would be surprised if like those aren't already tokenized. Um, I mean, it will only be able to do optimize like they probably have already done stuff like that, but it's like, you know, once you pick all the low-hanging fruits, you're left with like actually simulating a human programmer and having them like use English language or Chinese language to like write out their thoughts and then do optimization based off of that. Like that's what's actually happening. Oh, super important thing. This is the second thing I was going to mention. So you're familiar with the bitter lesson, right? Okay, so my original conception of bitter lesson is just let heck and stack more layers, but it turns out that's not true, right? Because if you just like naively did matrix multiplication based attention mechanisms, you have never gotten to GPT-2. Like even with, I think even with like modern hardware, it would be expensive to do, and it's like in order to get to GPT-2, you had to like actually understand the important parts of like context and attention mechanism. You have to like actually think things through and like find this highly optimized architecture that's like on one hand it's very elegant, right? On the other hand, it's counterintuitive because it's like, wait a second, like that's not very many interactions. Like, so it's like the bitter lesson isn't about like ignoring computational efficiency. It's about like understanding the system enough that you can actually optimize computational efficiency really, really well. And that enables you to stack layer upon layer. And that is what produces like the really good outputs. You know, like the bitter lesson isn't that you should try less. It's just you should try to like optimize your architecture and understand it on a deep level and like uh, that in a way that allows you to optimize your compute use such that you can like make these massive architectures that run efficiently and like produce incredible results and as opposed to like you know actually handwriting like activation functions well not activation functions but like handwriting you know what are they called positional embeddings were that's actually not a very good example. But like handwriting human knowledge, you know, what should you do when this chess piece is here and this chess piece is here? I've heard it. I think it costs like I'm spitballing here. I'm bullshitting. Like this is the mental motion for bullshitting, but like I might be right. It's somewhere between like $10 and $200 in cloud compute to train the largest models of GPT-2. For GPT-2 small, yeah, you can train it on like your desktop computer in like a couple hours, no problem. Mhm. A lot of the numbers are actually based off of previous transformer models, like um, the model from Attention Is All You Need also had 12 transformer blocks. Like it was like six encoders and six decoders, and also its conceptual embedding vectors were I think were also 768. I'm not 100% sure though. And it also used like 12 attention heads. But like so like it used that as a small OpenAI used that as the smallest version of GPT-2 like because it was just well that's a good starting place. They did some optimizations. A lot of it has to do with interactions with like I don't know with training data, the amount of training data you have, like the exact parameters what is it called meta parameters or hyper parameters used for training. I think the answer is quite a bit. It's, like just going to like 16 bits precision floats alone is significant. Like ultimately, like if you want to get GPT-2 small performance, I think you can like do it. We're at a point where you can like actually train it if you have a GPU in like a couple minutes. I think with all the optimizations. Yeah, I mean the really important thing about GPT-2 is that like they weren't trying very hard at all, even with the knowledge available to them at the time. They're just like, hey, look at this cool thing we could do. Because like every optimization you apply makes things slightly harder to understand. And GPT-2 is finally a conceptual model. It's like we apply all these optimizations, right? And just like look and we've made all these different sizes, just like and we want to make it easy for you to understand, so just look at it. See how cool it is. Okay. What do you think about the presentation overall? Like, I feel like no, first of all, I made a catastrophic mistake about dot products in the beginning. Surprised I didn't catch that. But other than that, like, how was the presentation overall? Hmm. 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 Yeah. 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 Okay. And one thing like I do get this vague vibe that you kind of don't think understanding technical information is important for safety work. Mhm, 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 mhm. And obviously my perspective is going to be different. It's like, other than the play, Miss Lincoln, Mrs. Lincoln, how was the oh well, no, it was like other than that, Mrs. Lincoln, how was the play, right? It's like in my mind, interpretability is like fundamental to how we solve the AI safety problem. So it's like, like in the models where, humanity survives this, like how much of a role do you think interpretability plays? Because a pause doesn't get you out of this. A pause still requires because a pause doesn't actually get you out of answering this question. You still have to solve the technical problems in the end. Mhm. On a somewhat related note, Soren, like I feel like the last couple of months, I've been kind of like, I want to, yeah, I've been kind of mean to you because I've been cracking jokes that are like, you know, targeted towards Danish people. Like, in my mind, it was like good natured, but I don't know how you're taking everything because like, okay, all right, all right, okay. Oh, next presentation. Mhm.